Murdo Station, Antarctica. Summer temperature -40 degrees Celsius. Winter -70. At those temperatures, steel shatters like glass. Engine oil turns solid. Diesel fuel becomes gel. And if a vehicle's engine stops running, if the oil inside freezes, if the fuel lines clog, if the hydraulics seize, it doesn't just break down, it dies. Permanently. So how do mechanics keep dozens of bulldozers, tractors, and trucks operational in an environment that's actively trying to destroy them? How do research teams hundreds of miles from base keep their machines alive through weeks-long expeditions? And what happens when the single system keeping every engine warm goes dark? This is the story of the daily battle to keep technology functioning at the bottom of the world, where every mechanical failure can cascade into a life-threatening emergency, and where the physics of extreme cold transforms ordinary maintenance into a fight for survival. The problem begins at the molecular level. When temperatures drop below -50 degrees Celsius, the materials that machines are built from undergo fundamental transformations. Standard-grade steel, the kind used in vehicle frames, bulldozer blades, and structural components, is normally ductile. It bends under stress. But at extreme cold, it undergoes what's called a ductile to brittle transition. The metal's crystal structure changes. A component that would flex or dent at normal temperatures will now shatter on impact, fracturing like ceramic. A bulldozer blade striking a hard patch of ice doesn't bend. It breaks. Catastrophically. Irreparably. Rubber and plastics fail the same way. Hydraulic hoses designed to flex as equipment moves become rigid. If you try to move them, they crack and split. Vehicle tires develop permanent flat spots where they rest against the ice, or the rubber simply disintegrates. Standard PVC-coated electrical wire, the kind in every normal vehicle, turns brittle. Bend it, and the insulation cracks, exposing the conductor. One short circuit can disable an entire electrical system. But the most immediate threat is what happens to fluids. Conventional motor oil thickens as it cools. At -50, -60, it reaches a consistency mechanics describes as jelly, or molasses, or solid wax. The same thing happens to hydraulic fluid, the liquid that powers every moving part in heavy equipment, from bulldozer blades to crane arms. It becomes so viscous that hydraulic pumps physically cannot move it through the lines. The equipment becomes inoperable. Every articulated joint, every lifting arm, every steering system, locked solid. Diesel fuel fails even earlier. At around -15 Celsius, cold, but nowhere near Antarctic extremes, diesel reaches what's called its cloud point. Wax crystals begin forming in the fuel. The liquid turns cloudy. Drop the temperature further, and you hit the pour point. The fuel gels into a thick sludge that clogs every fuel line, every filter, every injector. The engine starves. It cannot run. This creates an impossible situation. You need to start an engine, but the oil inside that engine is now a semi-solid mass. When you turn the key, the starter motor tries to crank the engine. The oil pump tries to circulate lubricant, but it's not pumping liquid. It's trying to force sludge through narrow passages designed for free-flowing oil. The pump strains. Sometimes it fails outright. If the engine does turn over, metal components begin moving against each other with inadequate lubrication. It's not gradual wear. It's immediate, catastrophic grinding. Metal scoring metal, bearings seizing, pistons scoring cylinder walls. Within seconds, the engine can suffer damage that would require a complete rebuild, if you even have the parts. The fuel system has already failed. Standard diesel has gelled in the tank, in the lines, in the filters. Even if the starter cranks and the oil somehow circulates, the engine cannot draw fuel. It cannot run. This is why, in Antarctica, a cold start is considered an engine death sentence. It's not a risk. It's a certainty. No vehicle is ever allowed to reach the point where its engine is truly cold, but running every vehicle 24 hours a day, 7 days a week, would consume an impossible amount of fuel. Fuel that must be shipped thousands of miles at enormous cost and stored in massive tanks that themselves require constant heating. There has to be another solution. The answer is centralization. The station's main diesel generators run continuously, not just during the day, not just during work hours, 24 hours a day, 365 days a year. They never stop. These aren't small backup generators. They're industrial power plants. And they don't just supply electricity for lights and computers. They are the thermal lifeline for every piece of machinery on the continent. Every vehicle, from the largest bulldozer to the smallest pickup truck, is equipped with an electric engine block heater. It's a small heating element embedded inside the engine block. When a vehicle finishes its work for the day and parks, the first action is always the same: plug it in. A heavy-duty electrical cable connects the block heater to the station's central power grid. The heater keeps the engine oil and coolant just warm enough to remain liquid. Not hot, not even comfortable, just above the threshold where the oil would solidify and the coolant would freeze. It's a constant, low-level heat input that prevents the cascade of failures that would otherwise occur within hours. But the generators do more than power block heaters. They're part of a system called combined heat and power. Industrial diesel generators are inefficient. Most of the energy in the fuel doesn't become electricity. It becomes waste heat. Normally, that heat is vented into the atmosphere and lost. In Antarctica, that heat is captured. The generators heat a loop of glycol, essentially anti-freeze, which is then pumped through insulated pipes called utilidors that run throughout the station. This heated glycol loop provides warmth to the residential buildings, the laboratories, and, critically, the massive vehicle maintenance garages. It also powers the snow melters that produce the station's drinking water. The waste heat that would be useless anywhere else becomes the station's circulatory system, and all of it depends on those generators running without interruption. Every morning at McMurdo Station begins the same way. The mechanics gather for a briefing. They don't start with the day's work orders or the vehicles scheduled for maintenance. They start with the vitals. Is the main power plant running? What's the fuel pressure? Are all 3 generators online, or is the station running on backup? What's the status of the water system, the pumps that move heated glycol to melt snow into drinking water? What about the wastewater treatment plant? These aren't routine checks. They're confirmation that the station's core life support systems are still functioning. Because if the main generators fail, if all 3 go offline simultaneously, the consequences are immediate and cascading. Every engine block heater goes dark. Every vehicle begins to cool. Within 2 hours, the oil in the engine starts to thicken. Within 4 hours, it's approaching the viscosity of jelly. Within 6 hours, those engines are no longer startable without risking catastrophic damage, and you cannot simply wheel them into a heated garage to thaw, because the garages themselves are heated by the same waste heat system that just failed. The station's water supply stops. The snow melters lose their heat source. Drinking water production halts. The heated glycol that keeps the wastewater treatment plant from freezing stops circulating. Pipes begin to freeze. The entire sanitation system is at risk. The residential and laboratory buildings lose heat. In the summer, when temperatures are only -30 or -40, the buildings might stay habitable for a day. In winter, at -70, they would become uninhabitable within hours. This is the nightmare scenario. It's why the generators are maintained obsessively. It's why there are multiple redundant units. It's why fuel delivery to the power plant is the single most critical vehicle operation on the entire base. And it's why, every single morning, the mechanic's first task is to confirm the heart is still beating. The station has a database. Every vehicle, every piece of equipment, every component is logged in a planned preventive maintenance system. Every part has a barcode and a known location in the warehouse. But the database cannot create parts that don't exist. Everything was ordered and shipped at least a year in advance, based on statistical predictions of what would fail and when. There is no next-day delivery. The next resupply ship arrives in a year. So when something breaks, and things break constantly, mechanics face a decision tree. The most common failures are manageable. Dead batteries are expected, cold drains them fast, and starting a diesel engine in extreme cold draws massive current. Batteries are stockpiled, expected. The lines flex and experience thermal stress. The garage has a hose building machine to fabricate replacements on site. Sensor failures are expected. Electronics don't like cold. Sensors are stocked. But a major component failure, a blown transmission, a cracked engine block, a failed hydraulic pump triggers a different assessment. The mechanics categorize vehicles. Critical equipment includes fuel transport trucks that supply the generators, snow melting equipment that produces drinking water, and fire trucks. Non-critical equipment includes backup bulldozers, secondary loaders, and spare cargo trucks. If a critical vehicle suffers a major failure and the replacement part isn't in stock, a non-critical vehicle is identified, parked, and cannibalized. Mechanics strip the needed component and install it in the critical vehicle. Every cannibalization is a gamble. You're betting you won't need that backup before next year's resupply. You're betting the remaining vehicles will hold together. You're betting the statistical predictions made a year ago were accurate. Sometimes you lose that bet. A traverse is a land expedition into the Antarctic interior. Teams use specialized tractors, often modified Caterpillar Challengers or Case STX quad tracks, pulling sleds loaded with fuel, equipment, and supplies. They're traveling to remote field camps, delivering cargo, or supporting deep ice drilling operations as hundreds of miles from any station. The convoy moves at 7 miles per hour. That's the maximum safe speed for heavy vehicles crossing unpredictable ice. A 10-hour driving day covers 70 miles. Then they stop for the night. And this is when the real work begins. The crew doesn't simply shut down the tractors and sleep. They execute a protocol. First, position the sleds and vehicles in a defensive formation, oriented to minimize wind exposure. Second, start the portable generator. Every traverse brings one. A smaller diesel unit mounted on a sled that serves as a mobile power source. Third, and most critical, plug in the engine block heaters. Every tractor has one. Heavy-duty cables run from the generator to each vehicle. The heaters activate. The engines, which have been running all day and are still warm, are kept warm through the night. Only after the engines are secured does the crew attend to themselves. They eat. They rest. They send their nightly situation report, GPS coordinates, weather conditions, fuel consumption, mechanical status, via satellite link back to the main station. The message confirms they're alive, their equipment is functional, and they'll be able to move again in the morning. Because if a tractor fails to start, if a block heater malfunctions, if the generator runs out of fuel, if a cable connection fails, the consequences are immediate. That tractor is now a 40,000-pound dead weight in the middle of the ice sheet. The convoy cannot tow it. They can't fix it on site. Complex engine repairs require a heated garage, specialized tools, and parts they don't carry. The options are abandon the tractor and continue with reduced cargo capacity, or call for a rescue operation, which means another team, more fuel, more risk, and potentially weeks of delay. Neither is acceptable, so the nightly routine is executed with precision. The generator runs, the cables are checked, the engines stay warm, and in the morning, when the crew starts the tractors, every one of them turns over, every time. That's not luck. That's the heated engine strategy working exactly as designed, but only if the protocol is followed perfectly. While mechanics fight to keep engines warm, scientists are fighting a different battle. Some of their instruments don't need protection from the cold. They need protection from heat. The South Pole Telescope and the BICEP Array are looking for faint microwave signals from the early universe, the cosmic microwave background radiation left over from the Big Bang. To detect these signals, the telescope's detectors must be colder than the environment around them. Much colder. The detectors are cryogenically cooled to 250 millikelvins. That's 0.25 degrees above absolute zero, minus 272.9 Celsius. The ambient air temperature at the South Pole, minus 70 degrees Celsius, is practically tropical by comparison. The extreme cold of Antarctica is actually an advantage. It makes the cryogenic cooling process more efficient. The dry air, the South Pole has less atmospheric water vapor than the Sahara Desert, also helps. Water vapor interferes with microwave observations, but this creates a different problem. The telescopes are so sensitive that even the faintest sources of heat or electromagnetic interference can ruin the data. The station itself is the enemy. The diesel generators produce heat and electrical noise. Vehicles emit exhaust and radio interference. Even human bodies radiate infrared heat. So the telescopes are located in the dark sector, a designated zone 1 kilometer away from the main station. No vehicles allowed, no radios, no Wi-Fi. The instruments sit alone in the dark and the cold, measuring signals that have traveled 13 billion years across space, and they cannot tolerate the presence of the machines that keep the humans alive. Other instruments face the opposite challenge. Hundreds of automatic weather stations are scattered across the continent, collecting temperature, wind, and pressure data. They're often hundreds of miles from any base. They must survive entirely on their own. During the Antarctic summer, when the sun never sets, they run on solar power charging rechargeable batteries. But when autumn comes and the sun drops below the horizon for the last time, the station switch to their winter power source, lithium thionyl chloride batteries. This specialized chemistry can operate at temperatures down to -55 Celsius with extremely low self-discharge. A properly sized battery bank can power a weather station for 6 months of continuous operation in total darkness. The electronics are sealed in airtight enclosures to prevent thermal pumping. As air inside heats and cools, an unsealed enclosure would breathe, sucking in moisture that condenses and freezes on circuit boards, destroying them. The wiring uses Teflon or silicone insulation because PVC cracks in the cold. Then the station is left alone, transmitting data every hour for half a year. If it fails, no one knows until the sun returns. 6 months of climate data, gone. None of this works, not the vehicles, not the generators, not the traverse tractors, without re-engineering the fluids. Antarctic vehicles do not run on diesel. They run on Jet A1, an aviation-grade kerosene designed for commercial aircraft flying at high altitude, or Special Antarctic Blend, a custom fuel mixture engineered specifically for polar operations. These fuels remain liquid and combustible well below -47 degrees Celsius. This is the single most important fluid on the continent. It powers the main generators, every vehicle, and the portable generators on traverses. If the fuel gels, everything stops. The lubricants are equally critical. Standard petroleum-based grease solidifies around -20 degrees Celsius. Antarctic equipment uses full synthetic lubricants engineered at the molecular level to resist thickening, often formulated with lithium complex thickeners that prevent hardening even at -54 degrees Celsius. These lubricants go everywhere. Metal moves against metal, wheel bearings, bulldozer track pins, hydraulic cylinders, gearboxes. Without them, articulated joints seize and bearings grind themselves to metal shavings. Hydraulic fluid presents another challenge. In heavy equipment, hydraulic systems power every moving part: the blade, the bucket, the steering. Standard hydraulic fluid thickens in the cold, becoming too viscous for pumps to circulate. Synthetic hydraulic fluid maintains its viscosity at extreme temperatures. But there's an additional consideration. Hydraulic lines rupture frequently. It's one of the most common failures. When a line ruptures in Antarctica, the fluid sprays onto snow and ice. Because the Antarctic Treaty designates the continent as a pristine environment, that contaminated snow must be excavated, packed into barrels, and shipped off the continent as hazardous waste. Many programs are now switching to biodegradable synthetic hydraulic fluids that still perform in extreme cold but break down naturally if spilled. Every fluid in every machine has been chemically re-engineered. The fuel, the oil, the grease, the hydraulic fluid, nothing is standard. These are specialized, expensive, purpose-built fluids designed to keep machines alive in an environment where the default state is failure. And even with all of that, the re-engineered chemistry, the heated garages, the block heaters, the combined heat and power systems, the daily preventative maintenance, the cannibalization triage, the nightly traverse protocols, machines still fail, constantly. The mechanics are not preventing failure, they're managing it. They're slowing it down. They're controlling where and when it happens, so that when a hydraulic line ruptures, it's on a non-critical bulldozer that can be parked and stripped for parts, not on the fuel truck that keeps the generators running. Because in Antarctica, the machines aren't just tools, they're life support. The generators keep the power on, the vehicles move the fuel, the snow melters make drinking water, the tractors deliver supplies to field camps. The fire trucks protect against the one disaster worse than freezing. If the machines die, the humans cannot survive, so the mechanics check the vitals every morning. They perform the scheduled maintenance. They rotate through the fleet, changing filters and fluids and belts before they fail. They plug in the block heaters every night. They keep the database updated. They make the triage decisions. They strip the parts from the dead to keep the living running. And the machines keep running, not because the environment allows it, but because humans refuse to let them stop.